Determined adversaries of the U.S. and our allies spend every day planning such threats as attacks on our nation's power grid infrastructure. Well organized and hidden within our own increasingly connected society, our enemies are facilitated by ever-growing communications networks that make it easy for them to disguise their intentions, movements, financial transactions, and social contacts. Tracking down adversaries through suspicious behavior in news, social media, and financial activity networks involves a level of complexity far beyond proverbial needles in haystacks. Now, a system created by HRL Laboratories has enabled analysis of data on a global scale to track down patterns of adversarial behavior before those behind it have a chance to act. The complex analytics of networks, or CANON, is a set of mathematical software tools that can merge and analyze massive amounts of open-source intelligence data to find patterns that reveal nefarious planning. Terrorist groups or individuals looking for avenues of attack, such as hacking the power grid, hide their electronic trails by spreading activities across many online domains and in many contexts. Such adversarial activity is nearly impossible to detect within isolated networks, but becomes detectable and recognizable when networks are analyzed together on a global scale. The technique is akin to seeing a map that reveals a pattern made by roads that is not visible while driving on the roads. The CANON tools can accomplish these analyses, flag questionable behavior patterns, and identify who the actors are. The CANON project is part of the Modeling Adversarial Activity Program funded by DARPA, the Defense Advanced Research Project Agency. With the project now entering its second phase, the CANON team will analyze networks of ever-increasing size with much greater detail. Scalability of CANON is of utmost importance, so in Phase 2, the team is improving the algorithms to handle exponentially larger amounts of data. The size and power required for these analyses will also require running CANON on a cadre of multiple computers working together on the program. The next problem the team must solve is handling the data's noise. In this context, noise is defined as missing connections, data errors, and missing or partial data. Even two different people having the same name can be read as noise to the system and cause data ambiguity. The HRL team is anticipating such noisy input records, so they are augmenting the mathematics to handle noisy data accordingly. A third emphasis for the team is giving CANON semantic reasoning ability on networks. This means understanding word meaning well enough to recognize when two described events are actually two different descriptions of the same event. CANON will then be able to merge or align those descriptions into a single event in a network with a world view. CANON uses a diverse set of synthetic networks or dummy data provided by DARPA to emulate real-world scenarios. In their Phase 1 research, the HRL team showed that CANON was effective. Using DARPA synthetic data, they tested the system on networks with millions of nodes. As they enter Phase 2, the team's challenge now is to show that CANON can find hidden patterns of adversarial activity within networks with billions of nodes. Success in this new phase will confirm CANON as a novel tool that exceeds the capabilities of any current software system for detecting adversarial activity. HRL's CANON system may soon lead the way in preventing possible terrorist attacks on U.S. infrastructure and will be helpful in tracking down other adversaries through detection of their electronic footprints, such as those left by money launderers, human traffickers, and drug cartels.